Hi guys, so today we're going to take a look at question 9 of paper 1 of the 2016 exam. Okay, so we have a pattern where a point moves 4 units from the origin in the positive direction along the x-axis. For the second stage, it turns left and moves 2 units parallel to the y-axis. For the third stage, it turns left and moves 1 unit parallel to the x-axis. At each stage after the first one, the point turns left and moves half the distance of the previous stage as shown. Okay, so now let's take a look at what they're asking us to do in part 1. How many stages has the point completed when the total distance it has traveled, okay, along its path is 7.9375 units. Okay, well, after the first stage, it's traveled 4 units. So let's call that S1, 4 units. In S2, it travels 2 units. In S3, it travels 1 unit. In S4, half a unit, because the distance it's traveling is decreasing by half each time. 0.25 units. 0.125 units. Okay, so let's just count these up. Okay, so after 1 unit, so let's call this D1, he's traveled 4 units. After 2 stages, he's traveled 4 plus 2, 6 units. After 3 stages, 4 plus 2 plus 1, 7 units. After 4 stages, 4 plus 2 plus 1 plus a half equals 7.5 units. After 5 stages, he's traveled 4 plus 2 plus 1 plus a half plus a quarter equals 7.75. Okay, so we're still not there. After 6 stages, we've traveled all these plus 0.125 equals 7.875. Okay, so we still haven't traveled far enough, so let's calculate how far he travels on the 7th go. Well, it's half of this again, so 0.0625 units. So after 7 stages, he's traveled this plus 0.0625, which equals 7.9375, which is exactly what we're looking for. So after 7 stages, it has traveled a total of 7.9375. So our answer is 7 stages to travel 7.9375 units. Now, that's a nice start to the question, just kind of get you familiar with this pattern and kind of what's going on. Now, on to part 2. Find the maximum distance the point can move along its path if it continues in this pattern indefinitely. Okay, so after 7 stages, it's reached 9.375, and it really seems to be slowing down. After 4 goes, it was at 7.5, and now after 7, it's at 7.9375. So it's really slowing down. So maybe it's approaching 8. So that might give us, if we calculate something and we end up getting 50, we might be a bit skeptical. So, well, let's look at this pattern here. We have 4 plus 2 plus 1 plus 0.5 plus on forever. And now the size of these are decreasing by a half each time. So we could say that this is 4 plus 4 by a half plus 4 by a half squared plus and so on and so forth. And now it really looks like a geometric sum, which we might expect. To be honest, whenever they ask you to do an infinite sum, it's probably always going to be a geometric sequence. And that when you read infinite sum, or when you read infinite sum or pattern going on indefinitely, you should probably immediately be looking for a geometric sequence. Okay, so well, what does a geometric sequence look like? It looks like a plus ar squared plus and so on forever, where a is our starting value and r is our ratio. So in this case, our starting value is 4 and our ratio is a half. It's decreasing by a half each time. And we have a formula in the log tables. The infinite sum of a geometric sequence is just a over 1 minus the ratio. So if we sub our values in here, we get 4 over 1 minus a half, which is 4 over a half, which is just 8. And this makes sense, as we were talking earlier. It does seem to be approaching 8, and so getting an answer 8 formally is it's very comforting. Okay, now on to part 3. Complete the second row of the table below, showing the changes to the x-coordinate the first 9 times the point moves to a new position. The first 9 times. Hence or otherwise, find the x-coordinate and the y-coordinate of the final position that the point is approaching if it continues indefinitely. Okay, so let's draw this little square here. Let's draw this little square here to just remind us what direction he's going after each go. Okay, so the first time he travels to the right, okay, and he travels 4 units, so we have this plus 4 here. So let's say S1 equals plus 4 horizontally. Then he turns left and goes half that distance, so he turns left. Now this square is not capturing the size of the distance, just the direction. So he travels half this distance plus 2 vertically because he's traveling upwards. So let's fill that in. Plus 2. Okay. Now he turns left from here, so now he's going to the left half of 2 units, which is just 1 unit. So S3 equals minus 1 horizontally. And now we're just going to continue this. he travels left, so now he's going down, and he travels 1/4 unit. So S4 gives us minus a half vertically. Sorry, not a quarter. Then he's back here, turns left again, so now he's again going this way. So S5 is half of a half, so 1/4 plus 1/4 horizontally. Sorry, let's go fill these into the table. So we have a minus 1/2 and then a plus 1/4. Okay, and now then he turns left and travels up half of a quarter. So S6 equals plus 1/8 vertically. Plus 1/8 in the tables. Then he travels to the left again. So now he's traveling left half of 8, which is 1/16. So S7 equals minus 1/16 horizontally. Then he travels, he turns left, and he travels half of 1/16, so 1/32 vertically, but downwards. Okay, and finally, S9, the 9th stage, he turns left again, and now he finishes off traveling positively in the x direction, half of 1/32, so plus 1/64 horizontally. So let's just fill in this table. So he goes minus 1/16 minus 1/32 and then plus 1/64, and then zeros elsewhere because if he's traveling horizontally, then he's traveling no distance vertically. So like on the first stage, he doesn't travel vertically at all. So now we want to find out the x and y coordinate of the final position. Okay, well, his x coordinate, so let's first look at the x coordinate. So it starts off at 0, it starts off at the origin, and then it travels plus 4 units to the right. We can just go by the table. Then it doesn't move, so we'll just ignore that. Then it travels minus 1 unit to the left, then plus a quarter unit, minus 1/16, and then plus 1/64. We're just following the tables. And then for the y coordinate, he starts off at 0 and then travels up 2, down a half, up an 8, again just following the tables, down 1/32, and well, I suppose both of these would continue in some form, and they'd continue forever. Okay, so well, what we said earlier was if they're talking about a sum, which we have here, is continuing forever, we should be trying to think of a geometric sequence. So how could we make a geometric sequence here? Okay, well, let's look at for the x coordinate. So geometric for x, well, a geometric is of the form a plus ar plus ar squared. Okay, so the first term is 4, and the second term is minus 1. So for it to be of this form, well, a would still be there, and this would be by minus 1/4. And then the next term would be 4 times minus 1/4 squared, which is actually exactly what it is. 4 times minus 1/4 squared is 1/4. And then 4 times minus 1/4 cubed is minus 1/16. So this pattern actually works. So we've actually constructed this geometric sequence where a equals 4 and r equals minus 1/4. Okay, and now let's try and do similarly. Well, first of all, let's see, where does the x-coordinate end up? Well, if we have our formula a over 1 minus r is the infinite sum. So if we do that for this, we would get 4 over 1. We would get 4 over 1 minus 1/4, which is 16 over 5. Okay, and now for the y-coordinate, let's try and do something similar. Again, we're looking for an a plus ar squared. So the first term is 2. And the second term is minus 1/2. So if we have 2 plus 2 times, well, what do we have to multiply by 2 to get minus 1/2? Well, again, we have to multiply by minus 1/4. And that'll give us 1/2. And then if it was geometric, it would continue minus 1/4 squared, which is exactly 1/8. And then 2 by minus 1/4 cubed is exactly minus 1 over 32. So again, we've sort of stumbled across this, the answer for the geometric sequence. So a equals 2 and r equals minus 1/4 again. Okay, so then if we use our formula for the infinite sum, we get 2 over 1 minus 1/4, which is 8 over 5. So the final x-coordinate, or the limit of the x-coordinate, is 16 over 5. And the limit of the y-coordinate is 8 over 5. And that's what they were looking for us to find. So that's just it. Alright, now on to part B. A male bee comes from an unfertilized egg. So he only has a female parent. Does not have a male parent, whereas a female bee comes from a fertilized egg, female parent and a male parent. Okay, so the following diagram shows the ancestors of a certain male bee. Okay, so that our certain male bee is this fellow here in the first generation, and the diagram goes back to G4. So let's just try and make sense of this diagram first. Okay, so we're starting off with a male bee, and so let's just write this down. Male bees, male, only a female parent. and female bees have female and male parents. Okay, so the bee that we're looking at is male, so that's why in G2 there's only a female parent, because he only has a female parent. And this female has both a female and a male parent, so that's why we get this G3, where the female has a female and a male parent. And now the female in G3 has both a female and a male parent, and the male only has a female parent. And now they want us to continue this diagram to the 5th generation. Okay, so the female, there's two of them. The females will have female and male parents. So let's fill that in now. So female and male, female and male, and the male in G4 will only have a female parent. So he will only have a female. Okay, so if we just draw our arrows just so that they know whose parents are whose. So our generation 5 will look like this. Now on to part 2. The number of ancestors of this bee in each generation can be calculated by the formula gn plus 2 equals gn plus 1 plus gn, where g1 equals 1 and g2 equals 1, which we can see in the diagram. So use this formula to calculate the number of ancestors in G6 and G7. Okay, so, well, let's write the formula that they've given us. So gn plus 2 equals gn plus 1 plus gn. Okay, so, well, let's start writing down the values of each gn. So g1 equals 1, g2 equals 1. We can just look at the diagram. G3 equals 2, g4 equals 3, and g5 equals 5. Okay, well, let's try and calculate G6. So G6 will equal G5 plus G4. So 5 plus 3. So G6 equals 8. And now G7 will equal G6 plus G5. And G6 we just calculated as 8, and G5 is 5. So G7 equals 13. And now you might actually notice something interesting here. Some of you might be familiar with this sequence. It's called the Fibonacci sequence, where the value of each term is equal to the sum of the previous two terms, and it's very closely related to the golden ratio, so which is a ratio about 1.618, which shows up, it's called phi or phi. Phi equals 1.618, and it shows up all over the place in nature. So the fact that it shows up here related to the ancestors of male bees is not that surprising, but still pretty cool. Now for the last part, the number of ancestors in each generation can also be calculated using the formula Gn equals 1 plus root 5 to the n minus 1 minus root 5 to the n all over 2n root 5. Okay, so it wants us to use this formula to verify the number of ancestors in G. So, well, if we just use this formula, so Gn equals 1 plus the square root of 5 to the power of n minus 1 minus the square root of 5 to the power of n all over 2n root 5. And we want to find G3. Well, it makes sense that we would just sub in 3 whenever we see n. And we would hope to get a value of 2. Oh, sorry. Equals, which does in fact equal 2. And now this formula, it might seem a bit weird, a bit random, but given this golden ratio that we mentioned earlier, it sort of makes sense because the golden ratio, it's about 1.618, but the exact way it's given is as 1 plus the square root of 5 over 2. So the fact that the formula for the number of ancestors looks like this is, again, not that surprising, but also pretty cool.